Alright, so number 6, it is a piecewise function. It is g of x. It says, again, use the definition of continuity to prove that the function is discontinuous. So one or more than one of those three rules can prove false, and it will be discontinuous. Again, just a reminder, if you want to be continuous, all three have to be true of those three rules. Alright, so we're going to look at a value of a. This is my x is equal to 3. Alright, so let's look at the first one. It is another rational function. I'm going to go ahead and factor out GCF-wise, an x on the top, and then a difference of squares on the bottom. You should see already there's another removable discontinuity. The removable discontinuity will occur at x is equal to 3. So what you're left graphing is x over x plus 3. Alright, so this one is not linear as the other number 5 was. Basically, after the removable discontinuity gets canceled out, I have this function here. Now, don't think that you can change this to x over x plus x over 3. That's not how you can divide fractions. It's only if you have one term on the bottom that you can separate this. Obviously, because we have more than one term on the bottom of this denominator right here, we're not going to be able to do that. So this one would be a calculator type of problem that you're going to put in to see what would the graph look like. So we come over here, control divide, and we're going to put x over, and I believe it was x plus 3. So let me go quickly right back. It is x plus 3. And then we can see what the graph is going to look like. The graph is going to, it looks like there is a vertical asymptote and a horizontal asymptote of some kind. If we come over here and we evaluate our reduced, we can see by Bobot-Neatz ratio, the exponents are the same, so y is equal to 1 is my horizontal asymptote. And setting the denominator equal to 0, my vertical asymptotes will yield x is equal to negative 3. So we are told to sketch the graph, so we're going to go ahead and now sketch this first piece of the piecewise function. So come over here, and we're going to put a vertical asymptote. The vertical asymptote will be at negative 3, so roughly about here. Whoops, let me grab a dashed line. And we'll put it about right here. And then we also will have a horizontal asymptote at y is equal to 1, which is about here. If we did this by hand, and you're wanting to do as much as you can look at this and say, if I plug in 0, what will for x, what will my y value be? Otherwise, my y-intercept. And you are going to get 0 because 0 divided by 3 would yield 0. So it will cross here. And then you could also look at what are the zeros of the function. Where will it cross the x-axis? Well, if I set the top equal to 0, it's going to cross the x-axis, and it's going to go through the origin. We are validating that with the graph itself, and it will look something like this. And in the top left, the top left is going to show that it's going to do this characteristic. Alright, so there's my graph. And we're trying to show that it's discontinuous at this x is equal to 3. So remember over here when we canceled, right here, there's our hole at x is equal to 3. Now the graph won't show it at x is equal to 3. It won't show a small little hole. But if we did go to the table, Control T, and we were just scrolling through, we could see at certain places it's not going to exist. So to validate this 3, I can go ahead and press Menu, Table, Edit Table Settings, and do the independent variable at ask, and I can say what is it going to be at 3. And by putting it at 3, we can see that it's, oh, hold on, it's not going to be 3, it's going to be a negative 3, that is. Sorry about that. Negative 3, it's going to be undefined. And you see that pound sign, it shows undefined. So at negative 3, which is right here, it's going to be undefined. Okay? So this comes from this piece right here that I've set equal to 0. The removable discontinuity at x is equal to 3 will exist also as far as a hole in the graph. Now, if I went back to the calculator and I did put 3, it would, if it was a point, it would exist at 0.5. Okay? So if I come over here, we know this right here is 1. We know this is 1 to negative 3. I'm saying here at positive 1, 2, 3, that there will be a hole in the graph. And the hole is going to occur right there approximately at x is equal to 3. And that y value, the calculator is saying that it would be at 0.5. Now this is a fancy calculator, remember? Other calculators may just show that it's going to be undefined and doesn't actually show a y value. This is a little bit more advanced, and it'll show you what the y value could have been had it existed as a continuous function. Okay, so I have my removable discontinuity hole, I have the vertical asymptote, the horizontal asymptote, and all this came from this rational function. Now all I have to do is graph the other piecewise function, which is at x is equal to 3, I'm just going to graph 1. So whenever I go to x is equal to 3, there would actually be a point here. And you see it's not going to cover this open circle. It's going to be a little bit above it. That open circle is at 1/2. This is at 1. Alright, so using the proof, I'm going to say, first rule, f of 3, the y value evaluated at 3, is going to use this equation. Not this one, because that's when it's not equal to 3. We're going to say this is equal to 1. Rule 2, does the limit exist? Well, the limit of f of x, as x is approaching this 3 that we're talking about, my at, is in fact equal to 1/2. 1/2 is what the y value would be. And obviously this is not going to equal this x approaching 3, which yields 1/2, does not equal the y value of 1. So 1/2 does not yield. And again, what would the limit be? I can use the calculator where I can see my simplified piece right here of x over x plus 3, and then just plug in the 3, because that's the limit that I'm evaluating. I would plug in the limit of this as x is approaching 3. Would give me 3 over 6, which is that 1/2. Alright, so therefore, you're going to say, there's the music. Therefore, f of x is discontinuous at x